So here we have a set, and we want to know what the span of the set is. So the span of a set, when I use the word span that way, it's a noun, because it's a something, it's an object. And the span of a set is all of the possible linear combinations of the elements of the set. So it's everything, in this case, that looks like something times the one vector plus something else times the other vector, which in this case would be all ordered pairs. So the span of L which some books denote by SPAN with like a function, the span of L is equal to all of R2. And we can also use the word span as a verb, so we can say L spans R2. So you take the elements, just these two elements can, using linear combinations, can build the entire vector space. So that's what it means for a set to span a vector space, is you can get everything in the vector space using just the elements in that set. And that's a fairly small set. It just has two elements in it, and it spans all of R2. And those two 2's are not a coincidence. So let's bump this set up. Just add one to it like we did in the linear independence video. I think it was 2, 3 I added. So look at this set M. This is also going to span R2, and it has to, because if a subset of the set already spans the vector space, you can add as many more as you want to, it's still going to span. Now, this set spans R2, it's not linearly independent. This set spans all of R2 and is linearly independent, so this is like the smallest set that you can have that will span all of that vector space. How about P equals 1, 5, and say 2, -1. Does this set, the set containing the vector 1, 5 and the vector 2, 1, does this span R2? Does P span R2? In order to know that, we'd have to take some general element in R2. So take x, y in R2. So there's a vector in R2. And we want to know if we can write this vector as a linear combination of these things. So can we find A and B so that A times 1, 5 plus B times 2, -1 is equal to x, y. So that's the question. And we can do this just like we have done these things before. I can do this scalar multiplication and then the vector addition, and I get A plus 2B and 5A minus B. We want for that to be equal to x and y. So that gives us a system of linear equations. A plus 2B equals x, 5A minus B equals y. And I'm pretty much stuck at this point because I have a general vector here and I have unknown coefficients there. And so how can I answer this question? Does this have a solution? Does this system have a solution? And the answer is yes, it does. Because if you look at the coefficient matrix, which is 1, 2, 5, -1, the determinant of that, 1, 2, 5, -1, is -1 minus 10 is -11, which is not equal to 0. So this is an invertible matrix, which means that this system has a solution. So the answer to this is yes, it has a solution. So no matter what general vector I take from R2, I can write it as a linear combination of these two guys, which means that P spans R2, or alternately that the span of P is equal to R2. And so this is another set. These two things span the entire set R2. Let's look at another set from of things from R2. Let's look at, what was that letter for that set? It was P, so let me take Q equals the set, say, 2, 5. So here's a set. It's a subset of R2. Does it span R2? And the answer is certainly not. There are plenty of vectors that I can't get by writing them as a linear combination of that one thing. So you can say no, I could take any vector that's just not a constant multiple of this, so like 1, well, let me take actually 2, 0. So I can't write a times 2, 5 is equal to 2, 0. It has no solution. So there are plenty of things in R2 that I can't write as a linear combination of the elements from Q. And if I even made that bigger, like if I had 2, 0, and 1, 0, and 3, 0, this set also doesn't span R2. Because there are lots of vectors that I can't write as a linear combination of these three guys. In fact, this set is in some sense very dependent because this is a constant multiple of this. They're all constant multiples of one another. And so there's a lot of dependence in this set. So it looks like you should get a lot of R2 out of here because you have 3 vectors to work with, but it really squishes down to just one vector because they're all multiples of each other. So that's span, and we can work with other vector spaces. So how about, does 1x squared span P sub 2? So this is a vector space we've looked at before. It's the set of polynomials of degree 2 or less, and the question is, does this set span all of P2? So could we get any vector from P2? Remember, vectors in P2 look like, you take something from P2, it looks like a plus b times x plus c times x squared, where c can't be, c can be 0, b can be 0, a can be 0, so it's polynomials of degree 2 or less. And it does span all of P2 because you can get anything that looks like this just by taking a times that plus b times that times c times that. So we have a set which we looked at in the previous video. This set is independent and it spans all of P2. And how about, let's consider the vector space of 2 by 2 matrices. How many vectors would we need in order to span all of this vector space? And I'll let you pause the video and think about that for a minute. And so we're back, and the answer is 4. Because we have 4 entries. So in some sense, this set of 2 by 2 matrices is just like R4. And so we could take the set that contains 0, let me put a 1 there, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So certainly this set would span all of the vector space that contains the 2 by 2 matrices, because any matrix that I wanted from that, say I wanted to build the matrix -2, 3, 5, 7, so this is a vector from this vector space, I'd take -2 times that, plus 3 times that, plus 5 times that, plus 7 times that. So this idea of span will be important in conjunction with linear independence when we talk about basis and dimension, but I will leave that for the next video. Okay, very good.